Hi everybody. I see we have a small audience today. I'm very happy to introduce our guest, Guy Dagan. He's doing his PhD now. That guy is doing his PhD currently in Weizmann Institute in the group of Professor Ilan Koren, and he will tell us about clouds. If you have any questions or comments or things that are not clear, please, I ask Guy and he's okay, please interrupt. The more you interrupt, the better the talk is. So don't hesitate. Thank you.
Yeah. Okay, so hi, thank you. So I'll present today our work which focused on aerosol effect on warm convective clouds, and I'll explain what I mean by that. But first I will start with a short general introduction. We know that most of the Earth's surface is covered by clouds. On average, about 60% of the Earth's surface is covered by clouds. And because of that, clouds play an important role in Earth radiation balance. Clouds interact both with the incoming shortwave radiation and with the outgoing longwave thermal radiation. The sun illuminates the Earth, and part of the incoming solar radiation is being reflected back to space. The part that is being reflected back to space is denoted as the Earth albedo. About two-thirds of the Earth albedo is determined by clouds. Okay, so a huge factor of the Earth albedo is caused by clouds. And the fraction that is not being reflected is being absorbed by the system and re-emit as thermal radiation, as long-wave radiation. On its way up to outer space, some of it is being absorbed in the atmosphere and re-emit back to the surface. This is the greenhouse effect. And clouds play also a role in the greenhouse effect of the Earth. So clouds are really an important player in Earth radiation balance. And because of that, small changes in clouds on the order of 1%, so those small changes in cloud properties or cloud coverage could be as important as the changes in greenhouse gases to the total radiation budget. Okay? So we need to understand cloud in very high accuracy in order to be able to predict future climate, for example. I told you in the title that we are focusing on warm convective clouds, and in clouds, warm denotes clouds that contain only liquid water and no ice, while mixed phase clouds or deep convective clouds contain also ice or mixed phase. And those clouds cover vast areas over the ocean and to less extent over land. The importance of the warm processes in convective clouds comes also from the fact that the warm processes in convective clouds are acting as the initial and boundary conditions for the mixed phase processes in deeper convective clouds. And so the understanding of the warm processes and, for example, the aerosol effect on the warm processes would be also a first stage toward the understanding of the mixed phase processes. Just to give you a flavor where one can find those types of clouds. So first of all, here we see them quite frequently. During the summer, if we have clouds during the summer, then most likely those would be warm convective clouds, those relatively shallow cumulus clouds. But in a global sense, they are more abundant at the subtropical regions, at the regions of the trade winds. We see here a schematics of the tropical circulation, the Hadley cell circulation. In the tropics, where the sea surface temperature is high, there is convergence of air and upward motion. Those would be deep convective clouds, which have a warm part at the bottom and a cold or mixed phase clouds at the upper part. The air subsidized at the subtropics, and in regions where the sea surface temperature is low, especially in the eastern boundaries of the continent where there is upwelling, we will find decks of marine stratocumulus cloud, those huge jacks of clouds that cover the entire sky. And moving with the returning branch of the Hadley cell in the trade wind regions, where the air encounter higher SSTs, the convection become deeper, and those would be the warm convective clouds that we will focus on. Okay, that all sometimes they are being called trade winds cumulus clouds. Because those clouds are part of the global scale circulation, or in this case, the tropical scale circulation, changes in them, for example, due to changes in aerosol concentration, could change also the global scale circulation. I mentioned it already, but just to be clear, what are aerosols? So aerosols are solid or liquid particles that are being suspended in the atmosphere, and they can be caused due to natural or man-made reasons. They have natural or man-made sources. A few examples of natural sources. So desert dust is the largest source of natural aerosols in the atmosphere, at least by mass. Volcanic eruptions also release a huge amount of aerosols to the atmosphere. Over the ocean, breaking of waves release sea salt aerosols to the atmosphere. And this would be the most abundant type over the ocean. Also, biology release aerosol to the atmosphere, for example, pollens. But now we know, and Yoav can tell you more about it, that the biology in the ocean, the phytoplankton and the viruses in the ocean also release aerosol to the atmosphere and can interact with clouds. A few examples of man-made aerosols. So every burning of fossil fuel release aerosol to the atmosphere. So industry, cars, ships, airplanes, and so on will release aerosol to the atmosphere. And another man-made source of aerosols is man-made forest fires that also release a huge amount of aerosols to the atmosphere. Okay, and what is the connection between cloud and aerosols? So the initial connection between cloud and aerosols comes from the fact that aerosols serve as cloud condensation nuclei. In order to form a cloud droplet, the water vapor needs to condense on some surface area, and aerosols are acting as this surface area that is available for condensation. In theoretical atmosphere with no aerosols, okay, this is not the case in our atmosphere, but in a theoretical atmosphere with no aerosols, there would be no clouds or almost no clouds. We will need to get to very high supersaturated conditions in order to form cloud droplets. And because of that, the aerosol properties, the chemical properties, and the physical properties, the total concentration and size distribution, determine the initial droplet size distribution in the cloud. And the initial droplet size distribution in the cloud determine many of the cloud processes. So it raises the question, do we influence cloud by this pathway? Okay, we saw that we influence the budget of aerosols in the atmosphere, and aerosols interact with clouds. So do we have an influence on the cloud properties by this pathway? And obviously, the answer is yes. And I think this is a very straightforward, clear example to see it. You know what we see here? You know what it is? So it's like contrails of planes, but in this case, it's ships. Ships that sails in the ocean. These are ship tracks. The ships burn fossil fuel, release aerosols to the atmosphere. The aerosols interact with the clouds, and in regions where we have more aerosols, we will have more cloud droplets. And for a given amount of liquid water in the cloud, increasing the amount of droplet increases the reflectivity of the clouds. The cloud become more reflected. They reflect more of the incoming solar radiation. And this is why we see them from space brighter. Okay, this is a satellite image over the ocean, and we see the ship tracks brighter from space. If they are brighter and reflect more of the incoming solar radiation, then what would be their effect on the climate, on the radiation balance? They would act to cool the system, okay? Less radiation is being absorbed by the system, more is being reflected, so it would act to cool the Earth. But in this case, it's very easy to see it and even to calculate and constrain it, but trying to estimate the global effect of cloud aerosol interaction on the radiation is a pretty hard job, and you can see it from here. This chart is being taken from the IPCC report, and it presents all the radiative forcing components due to anthropogenic activities. Radiative forcing means an imbalance on the natural radiation budget of Earth. Positive radiative forcing would lead to warming of the system, while negative radiative forcing would lead to cooling. And you see here all the radiative forcing component, and at the bottom line we see the net effect, okay, the total effect. And as we know, the net radiative forcing of anthropogenic activities is positive, meaning that, in general, we act to warm the Earth by about 1.6 watt per meter square. But it has a huge uncertainty. Okay, it could be all the way between 0.6 to 2.4. And the fact that we cannot constrain very well the net radiative forcing makes us life hard in trying to predict the future climate. Okay, this is one of the most basic questions in regarding to global warming, what we are doing to the system. And if you look on the component of this total effect, then you'll see that most of this positive effect comes from the first two lines. Those are the greenhouse gases, and especially from the carbon dioxide, which its magnitude is the same as the total, more or less, 1.6. But in this case, the uncertainty is quite small. Okay, so we understand pretty well the CO2 effect on the climate. So where does all the uncertainty in the total effect comes from? It mostly comes from this line. And this line is exactly the cloud-aerosol interaction effect on the climate. You see that it is estimated to be negative, meaning to counteract some of the greenhouse effect by about minus 0.7. But it has a huge uncertainty, and it could be something which is pretty close to 0. But at the same time, it can be something which is negative but larger in magnitude than the CO2 effect, okay, to counteract the entire CO2 effect. And in our group, we work exactly on this line, trying to understand better the processes behind the cloud-aerosol interaction and to hopefully estimate it better and constrain the uncertainty better in this case. And why it is so hard to estimate the global mean effect on the radiation of cloud-aerosol interaction? Partially, it is because some of the key cloud microphysical processes shows contradicting dependency on the initial aerosol size distribution. For example, under polluted conditions with more aerosols, initially there would be more and smaller droplets. And this means that the total droplet surface area would be larger, because we take the same amount of water and divide it on larger amount of droplets, so the total droplet surface area increases. And the diffusional processes in the clouds of condensation and evaporation are proportional to the total droplet surface area. So under supersaturated conditions, like can be found in the cloud core, there would be more efficient condensation or faster condensation rate. While under subsaturated conditions, like can be found in the cloud periphery, there would be more efficient evaporation. Okay, and this contradicting effect of cloud-aerosol interaction, or the contradicting effect of aerosols on the processes in the clouds, can be scaled up to the total effect, to the total sign of the effect even. And what you see here is previous literature from the last 12 years or so, and it shows that it doesn't even agree on the sign of the total effect. Some previous studies have shown that aerosols can lead to warm convective cloud invigoration, meaning that the cloud would be more developed, both vertically and horizontally. The cloud will contain more liquid water and eventually precipitate more. But on the other hand, some previous studies have reported on cloud suppression, meaning that under polluted conditions with more aerosols, the clouds would be shallower, less developed, will cover less area, and eventually will precipitate less. And I hope that the result I'll present today could resolve this contradiction between previous studies. Okay, so now I'm getting to talk a bit about our work. And at the first stage, I would like to present an observational-based study. in which we used satellite observations of the atmosphere over the ocean. And we focused on the cleanest areas over the globe. We focused on the marked areas over here. All of them were over the southern oceans. And they were, sorry, the map that you see here is a map that presents the mean AOD. AOD is aerosol optical depth. It's a measure of the amount of aerosols in the atmosphere from remote sensing. And we focused on those areas that had a mean AOD of less than 0.1. The most clean areas that one can find over the globe. And the idea of focusing on such clean areas was that some of the key microphysical processes shows the highest sensitivity to changes in aerosol concentration in the transition between extremely clean to slightly polluted. And indeed, we saw a very high sensitivity to changes in aerosol concentration. Moving right here means that the AOD is increased or the aerosol concentration is increased. And in those regions, we saw that increasing the aerosol concentration result in stronger rain rates. Clouds that were more vertically developed enhanced their top reach higher in the atmosphere. And they also were more horizontally developed, and hence they cover larger areas, or the cloud fraction, the fraction that is being covered by clouds was higher. And this is a very clear evidence for warm convective cloud invigoration from observations, okay? And the main conclusion from this paper was that warm convective cloud invigoration can be seen as a direct continuity of the concept of aerosol-limited clouds. Under the concept of aerosol-limited clouds, the cloud development is thought to be limited under extremely clean conditions because the condensation is not efficient under those conditions. And in addition, precipitation starts very early under clean conditions. The precipitation depletes the water from the cloud and prevent further cloud development. Adding aerosols to those types of cloud will result in cloud invigoration. The problem is that for this relatively narrow range of aerosol concentration, even 0.2 or 0.3 is relatively clean conditions. So this range of aerosol concentration that was examined here is pretty narrow. And for this relatively narrow range of aerosol concentration, we do not know whether this trend will continue, saturate, or even reverse. So in order to examine it and in order to understand better the processes behind it, we went and used numerical simulations. And at the first stage, we used a single cloud numerical simulations. We used the Tel Aviv University axisymmetrical cloud model. And we initialized the model with 9 sets of initial conditions, initial atmospheric thermodynamic conditions, in which we changed the inversion base height for 3 different levels. Inversion layer in the atmosphere is a very stable layer in the atmosphere in which the temperature rises with height. And many times, the inversion base determines more or less the cloud top, because it's hard for the cloud to penetrate and develop above this very stable layer. So by increasing the inversion layer, the inversion base height, we actually increase the potential of the cloud to develop, okay? In addition, we also changed the relative humidity in the cloudy layer for 3 different levels. And again, increasing the relative humidity in the cloudy layer increases the potential of the cloud to develop. For each set of initial atmospheric conditions, initial thermodynamic conditions, we simulated 10 different simulations with 10 different aerosol concentrations, spanning very large range, starting from extremely clean cases to highly polluted cases.
Can you give us a feeling on what this number represents?
Okay, so yeah, 5, it hardly can be found in the atmosphere. The cleanest areas we found were around 10, order of 10. So 5 is extremely clean.
With particles per centimeter?
Yeah, aerosols per cubic centimeter. Yeah. And 10,000 is like Beijing or something. It's extremely polluted. Okay?
And
Yes?
you check a few kinds of aerosols, like the hydrophilic
Yeah, so, okay, so let me show you the first result slide, and then I'll explain what the chemical... We did two types of aerosol chemistry. The chemistry is less important in this case. I'll show you what it does in a minute. Just to sum up the simulation that we did, the initial condition that we used 3 different levels of inversion base height, 3 different levels of relative humidity in the cloudy layer. Those were the meteorological conditions, if you want. And the microphysical conditions were 10 different levels of aerosol concentration. So altogether, we had 90 different simulations. And now we see the result. We see here the maximum liquid water mass that was produced during the cloud evolution as a function of aerosol concentration. Each curve here represents one initial conditions with given inversion base height and given relative humidity in the cloudy layer. And you see that for all initial conditions, we get this non-monotonic behavior, this boomerang-shaped behavior. Starting from the extreme clean case and adding aerosols result in more mass being produced in the cloud, or in other words, cloud invigoration. And this positive trend is with agreement with the observational-based study I just presented earlier. And this positive trend continues up to an optimum aerosol concentration that correspond to the maximum mass that was produced for given initial conditions. And above it, additional increase in the aerosol concentration result in less mass being produced in the cloud, or in other words, cloud suppression. So we see that for all initial conditions, both cloud invigoration and cloud suppression are a possible solution. Okay, and this goes to the contradiction in previous studies I showed you earlier. And another thing we can see from here is that the optimum aerosol concentration depends on the initial conditions. For deeper clouds and higher relative humidities, the optimum aerosol concentration was lower, while decreasing the relative humidity or decreasing the cloud size decreases the optimum aerosol concentration. So this is for a given chemical composition. If we change the chemical composition, the only thing that we get the same general trend, but it shifts a bit. So if you increase the hygroscopicity of the aerosols, then the optimum would be at actually lower values, because you need less aerosols in order to consume the same amount of water. So the general trend remains the same, but it shifts a bit. And in order to explain the existence of the optimum aerosol concentration, we need to analyze the temporal evolution of the main processes in the cloud. And two of the main processes in the clouds are, first of all, the diffusional processes of condensation and evaporation. And secondly, the second most important process in clouds is the collision and coalescence, or collections of droplets. In order to form large raindrop, many small cloud droplets need to collide and form large raindrops that could fall down as rain. So the collision coalescence mark the initialization of rain processes in the clouds. And in this figure, we see the phase space that's spanned by those two processes. In the x-axis, we see the condensation, and in the y-axis, we see the collision coalescence, or the collection mass. Each subplot represents different aerosol concentration, and the curve represents the evolution or the trajectory of the cloud on this phase space. Okay, the cloud starts from from here and evolve on this phase space. And if we look first on the extreme clean case, we see that the trajectory is diagonal from the very beginning. This means that once the clouds start to form and condense water and move right on this phase space, it also started to have a significant amount of collision coalescence, and hence moved up on this phase space. This is why the trajectory is diagonal, okay? And in this clean case, the collision coalescence was not, the condensation processes was not efficient from the beginning, because it is a clean case and the total droplet surface area was low. And the early initialization of collision coalescence reduced even more the total droplet surface area. So both effects together resulted in non-efficient condensation in this case. we see that the cloud did not reach high values on the x-axis here. Increasing the aerosol concentration increases the condensation efficiency and delay the initialization of collision coalescence. We see that the clouds start to move up on a later and later stage as the aerosol concentration increases. Going to very high aerosol concentration, we see that the cloud grow by condensation, reach its maximum mass before any significant amount of collision coalescence was seen. Then it starts to dissipate, to evaporate water and move left on this phase space. And only at the very end of the cloud evolution, some, or even none in extreme polluted case, collision coalescence was seen. So in those clouds, in very high aerosol pollution, the collision coalescence was delayed so much to after the peak in the cloud mass. Okay?
This interpretation is just, you don't see it explicitly in the model, right?
I do. This is the result from the model.
This is the result, but the explanation is, it's not explicitly...
So we guess from the model that the initialization of collision coalescence is delayed. Yeah. With the initialization time of collision coalescence is delayed with aerosol concentration from the model, and it's well known. It's not our result, but the interplay with the time of condensation determine the total amount of water, because in clean clouds where you have very early initialization of rain processes, then the cloud would not precipitate that much because it did not condense a lot of water. The collision coalescence started too early to interrupt the diffusional growth. In polluted, extreme polluted clouds, the cloud would not precipitate that much because the collision coalescence was delayed so much to after the peak in mass, and the cloud lose mass by evaporation before collision coalescence was seen. And the optimum aerosol concentration, which correspond to somewhere between those two marked cases, is the optimum because the collision coalescence started at the right time. Okay, the cloud grow by condensation, reach its maximum mass, then exactly at the right time when having maximum mass, collision coalescence started and it started to move up on this phase space, and hence produce the maximum amount of rain. Okay, so the optimum aerosol concentration correspond more or less to an orthogonal behavior on this phase space. So you don't want the collision coalescence to start too early to interrupt the diffusional growth. You don't want it to start after the diffusional growth. You want it to start exactly at the right time when you have maximum mass in the cloud. Okay, so far I presented results from single cloud simulations. Now I would like to move to the larger scale of a cloud field. And in a cloud field, we are talking about a few tenths of kilometer domains in which many clouds are being formed at the same time. For this case, we use the SEM-LES model. This is how a cloud field simulations look like. And by using a cloud tracking algorithm that was developed in our group, we can follow the cloud evolution from the moment that they were formed till the moment they dissipate. And we can follow them even if they split or merge with other clouds. And this is the color code that you see here. The blue clouds are proto-clouds that just form, while the green and red clouds are clouds that went through splits or merge, respectively. And I brought you this example, first of all, that you could see how a cloud field simulations look like, but mostly I wanted you to see how complicated things can get in a cloud field. You see that most of the clouds are either green or red. And if you follow one cloud, you'll see that many of them goes between green and red back and forth. This means that the level of interaction between the clouds is pretty high. Okay, so we include now many additional levels of complexities above the single cloud simulations. But nevertheless, even though that we included all of those additional levels of complexities, we still get this non-monotonic behavior that we saw on the single cloud scale. Okay, we see here a few of the mean cloud field properties like total mass, liquid water pass, cloud fraction, cloud top, and so on. And we see this non-monotonic behavior that we saw on a single cloud scale with first cloud invigoration, then optimum aerosol concentration, followed by cloud suppression. And I would like now to show you evidences that this contradicting effect is this non-monotonic trend is as a result of contradicting effect of aerosols on the warm convective clouds, of two positive effects of increasing the condensation efficiency and increasing the droplet mobility, versus two negative effects of increasing the evaporation efficiency and water loading. In a minute, I'll explain everything that is written here. Regarding the condensation efficiency, we see here a vertical profile of the mean condensation rate. Each color represents different simulation with different aerosol concentration. So we average over all supersaturated areas in the domain, and we see a very significant increase in the condensation rate with aerosol loading. The same goes to evaporation. If we average over the subsaturated areas of the domain, we see a very strong increase in the evaporation rate with aerosol loading. So both condensation and evaporation rate increases with aerosol loading because of the increase in total droplet surface area. Regarding the water loading effect, you see here vertical profile of the mean liquid water content, meaning the amount of liquid water that the cloud carry with it. And you see again an increase in the mean liquid water content with aerosol loading. As I showed you, under polluted conditions, there is an increase in the condensation efficiency, and also there is a delay in the initialization of rain processes. So both effects together result in polluted cloud being carry more mass for a longer time, and this extra mass that the cloud need to carry with it reduces some of the cloud buoyancy. Okay, it acts to suppress the vertical development of the clouds. But nevertheless, even though that the extra mass reduces the cloud buoyancy, when we look on the average air vertical velocity in the domain, we see an increase in the air vertical velocity with aerosol loading because of the increase of the latent heat, because of the increasing condensation efficiency. So air vertical velocity is extremely important factor in convective cloud. Okay, this is the driving force behind convective cloud. So this would be probably the first thing to look at. And we see an increase with aerosol loading, as I said, because polluted cloud condense more efficiently the water. The condensation released latent heat, which fueled the cloud development. However, the air vertical velocity, important as it is not the only important factor, vertical velocity quantity to look at. We need also to consider the droplet vertical movement compared to the air. Droplet fall, always they have always negative velocity, and they do it in a way that large droplets fall relatively fast, while small droplets have more or less negligible falling velocity. And here we calculate eta, which is the effective terminal velocity. It is the mass-weighted mean terminal velocity of all hydrometer in the domain. It's a measure of the collective velocity of the droplet compared to the air. And we see that under clean conditions, the droplets fall relatively fast. Okay, they have a negative but relatively large fall velocity, while under clean conditions, the fall velocity is pretty negligible. This means that the droplet move better with the ambient air. Okay, they move with the air vertical velocity and don't have a relative velocity compared to the air. So, and this is what we define as increasing droplet mobility with aerosol loading. Increasing the aerosol loading increases the droplet mobility, and at the same time also increases the air vertical velocity, and both effects together result in more mass, more liquid water mass being pushed higher in the atmosphere, and hence the center of gravity of the clouds increase with aerosol loading, or the cloud top, if you want, increase with aerosol loading. Okay, I didn't mention it so far, but the result I presented from the cloud field simulations were based on 16 hours of simulations, and we averaged the result over the last 14 hours of simulations. Okay. So we excluded the first 2 hours, which were the spin-up time. It takes time for the cloud field to form, and we average over the last 14 hours of simulations. But many times, during these 14 hours, there is some trend in the property that we average on. And you can see an example of it here. This is the mean cloud top for a polluted simulation as a function of time. And you see that there is some trend during the simulation. The cloud top becomes deeper with time, okay? And in order to take it, and when we average over the entire 14 hours, we do not take this trend into account. So in order to take it into account, we will now divide the simulation to 3 parts and look on the mean of each part separately. In blue, we'll see the mean over the first part, in green the second, and in red the last part. And so this is what we see here. We see the same cloud field properties we saw earlier, but this time divide to 3 parts. And we can see that in most cases, during the simulation, between the blue, green, and red, there is a decrease in the mean cloud field properties under clean conditions, while there is an increase in the mean cloud field properties under polluted conditions. And the fact that under clean conditions there is a decrease with time, while under polluted conditions there is an increase with time, also derive an increase in the optimum aerosol concentration. The concentration that mark the change in the trend increase with time. You can see it here that the peak shift to the right between the blue, green, and red. Okay, the optimum aerosol concentration increase with time. And why is that? This is because clean and polluted clouds interact differently with the thermodynamic conditions of the environment. We see here a vertical profile of the mean change in temperature vertical profile and in water vapor mixing ratio or humidity vertical profile as a function of aerosol concentration. Okay? Let's focus first on the clean half of this chart. We see that under clean conditions there is warming of the cloudy layer. In our simulation, the cloudy layer span between 500 meters and 1,500 meters. So the cloudy layer becomes warmer with time, while the subcloud layer becomes colder with time. And the cooling of the subcloud layer was accompanied by increasing the humidity at those levels. On the other hand, under polluted conditions, there was a strong increase in, there was strong cooling of the upper cloudy layer and inversion layer, which was accompanied by increasing the humidity at those levels. Changes in the thermodynamic condition, the temperature and humidity, are driven by changes in condensation evaporation. And in this figure, we see the net vertical profile of condensation evaporation rates. This example is for a clean simulation. And we see here the net condensation evaporation vertical profile for the entire domain for the entire time.
Can you explain condensation?
So in each layer you have both condensation and evaporation. We average it all, and we see what is the net effect. If you have net condensation, okay, so in this case, no, it's condensation in mixing ratio per second. So how much mixing ratio of water vapor went to liquid water in each second? So in this clean case, we see net condensation in the cloudy layer. And net condensation means that this cloudy layer, this layer would become warmer with time because of latent heat release, while there is net evaporation and cooling of the subcloud layer. Okay? In this simulation, the water was condensed in the cloudy layer. They sediment down as rain and partially evaporate below cloud base. Okay? Stop me if it's not clear, okay? The end result of it on the thermodynamic is warming above cooling. Okay, this is the dipole in the thermodynamic. And this means that the thermodynamic lapse rate, the thermal instability, become more stable with time. Okay, if you warm upper more than below, you make the atmosphere more stable. And this means that under clean conditions, the clouds act to consume the thermodynamic instability that created them. On the other hand, under polluted conditions, the dipole is exactly the opposite. We have net condensation in the lower cloudy layer and net evaporation and cooling of the upper cloudy layer and inversion layer. So in this case, the the end result, in this case, the water is being condensed at the lower cloudy layer. And as I showed you earlier, there are stronger air vertical velocities that push the water higher in the atmosphere. There, it evaporates more efficiently. And the end result is warming below cooling and destabilization of the thermal upside, meaning that the thermodynamic instability increases with time. Okay, it's a very interesting case in which the cloud acts to increase the thermodynamic instability that created them. It's a positive feedback. I hope I didn't lose you too much.
So you have a negative feedback over there. On the left, it's a negative feedback, and on the right, it's positive.
Right, exactly. This would act to kill the cloud eventually, and this would act to make them invigorated. No, so here you have condensation above evaporation, and here you have condensation below evaporation. So one time you cool below warm, and one time you warm below cooling.
So the left case belongs to the previous class?
Yeah, this is for the clean case, and this is for the polluted. In polluted cloud, the dipole of warming and cooling is in a way that you kill the thermal upside, you kill the thermal instability, while in polluted cloud, you increase it with time. Okay, and this is exactly what we see when we follow the thermal lapse rate with time as a function of aerosol concentration, both in the cloudy layer and in the subcloud layer. In this figure, the black line represents the initial conditions, which were equal for all simulations, and the blue line represents the final conditions after 16 hours of simulation. And we see that both in the cloudy layer and in the subcloud layer, the thermal lapse rate become more stable with time under clean conditions, while it becomes more unstable with time under polluted conditions. Okay? And the fact that under clean conditions, the cloud consumes the thermodynamic instability derive exactly the decrease in the mean cloud field properties I showed you earlier. Okay? The cloud act to kill themselves. Okay? While under polluted conditions, the fact that the thermodynamic instability increases with time derive the increase in the mean cloud field properties with time. And both effects together derive the increase in the optimum aerosol concentration with time. Okay, so let me sum up. We showed the non-monotonic behavior both on the single cloud scale and on the cloud field scale. And as I mentioned, this could resolve previous inconsistency between previous studies that some of them reported on this branch and some of them reported on that branch. And here we see that both branches are possible. And we explain the existence of the optimum aerosol concentration based on analysis of the temporal evolution of two of the main processes in the clouds. And we showed that the optimum aerosol concentration corresponds to initialization of rain at exactly the right time when the cloud have its maximum mass. And on the cloud field scale, we showed that clean and polluted cloud interact differently with the thermodynamic condition in a way that clean cloud consume the thermodynamic instability and eventually act to suppress cloud development, while polluted conditions act to increase the thermodynamic instability and create more deeper and more vigorous clouds with time. I hope I didn't kill you too much. For that, I'll finish. And thank you very much. And be happy to take any questions if you have.